Okay, we're going to continue our discussion of finding limits algebraically by looking at more cases of 0 over 0. So first example, let's look at the limit as x approaches -4, and we have a complex fraction. All right, so exactly what we reviewed right at the beginning of this lesson segment. And to simplify this complex fraction, the numerator is my problem, right? Not really the denominator. I don't have a fraction within the denominator. So I just look at the least common denominator for the numerator, which would of course be 4x. So again, I'm going to multiply my expression by 1 so that I only change the appearance and not the value. So I'm going to multiply it by 4x over 4x. All right, and if it helps you, you can do 4x over 1 divided by 4x over 1. All right, so we distribute that in. And this is a wonderful method to use because in one quick step, right, the 4x divided by 4, that would leave me with just x. Distribute this in, 1 over x times 4x leaves me with 4. And then in the denominator, I would get 4x times x plus 4. And it's very tempting. I know your training tells you to immediately distribute. But I always tell students on these exercises, don't be too quick to distribute or to FOIL, because what we're hoping for is something to cancel. So if you distribute this in, you would just later need to factor it back out. Because notice when I write it as a product of two factors, these cancel. All right, so now, and notice the x plus 4, if I plug in -4, that would give me 0 over 0. So again, that problematic 0 over 0 factor cancels. I'm left with only 1 over 4x, plug in -4, and I get -1 over 16. Now another example, as I mentioned in the beginning of the segment, is that sometimes we would be rationalizing the numerator, not necessarily the denominator. So if I asked you to find this limit, the limit as x approaches -3, and again, if I try direct substitution, right, if I tried it in the problem above, or if I try it in this problem, I end up getting 0 over 0. Obviously, the denominator would be 0 if I plug in -3 for x. The numerator would give me 9 minus 5, which is radical 4, which is 2. 2 minus 2 is 0. So, of course, I would get 0 over 0 if I tried direct substitution. So, my best option is to change the appearance without changing the value by multiplying by 1. And anytime you have an expression with a radical, you should immediately think of the conjugate, using the conjugate. So the conjugate in this case would be 2 plus radical x squared minus 5. And I have to multiply by 1, so luckily this whole thing divided by its equal gives me 1. And multiply that out. And there's a very, very common mistake that students will make here. So when I FOIL, my first gives me 4. Inside, outside, that's the whole beauty of the conjugate. This plus this, right? One's positive, one's negative, that will give you 0. The inside, outside would always give you 0. And then last, will I multiply something by radical x squared minus 5 by radical x squared minus 5. right? Just leaves me with x squared minus 5. Where you have to be careful is because we get a negative. Negative times a positive is negative. So we want to, because we have an entire term here, we need to distribute the negative through. All right, so it's important to have parentheses there. Then, in the denominator, as I said earlier, don't be too quick to just distribute, right? Because what we're going to hope for is something to cancel out. So in this example, if I keep going, distribute that negative. So that would give me, and I should keep writing x approaches negative 3 at every single step. That would give me 4 minus x squared plus 5 over, and I'm not going to keep writing that whole denominator, right? But that whole thing stays in the denominator. So if I combine here, I get 9 minus x squared over x plus 3 times all this. And now I can factor. So that would factor into 3 minus x, 3 plus x. And as I mentioned, we're looking for something to cancel. And luckily it does. So these would cancel. Then I'm finally left with the limit as x approaches negative 3. I can plug in negative 3 for x. Let me write it like this, of f of x equals 3 minus negative 3 over 2 plus, so that would be 9 minus 5. Denominator would be 4, numerator would be 6, 3/2. Right, so before I end this segment, let's take a look at a graph, right? So this is working with limits algebraically. So in this segment, let's take a look at limits graphically. And here I've graphed the function f. And if I were to find the limits as, so over here in the right-hand corner, let me pull this down so we can see the directions. It says find the limit as x approaches negative 2 from the left and from the right. So what I have to think about in this case is if I were walking along on the x-axis, right? And if I were walking along here, approaching negative 2 from the left-hand direction, and I'm walking along and I'm looking down at these functional values down here. And what I'm seeing is I'm seeing functional values. It doesn't matter that I have an open circle here when I get to negative 2. Remember, to find a limit as x approaches negative 2 from the left, I never actually step right on negative 2. I just walk up to it. I get closer and closer from the left-hand side. And as I do that, I can see functional values here that are getting closer and closer to negative 3. All right, so my limit as x approaches negative 2 from the left would be negative 3. But if I were to walk up to negative 2 from the right-hand side, all right, so here I am walking along the x-axis from values greater than negative 2, and I'm looking down at the functional values, and in this case, I see functional values getting closer and closer to, so we'll round to the nearest whole number. My diagram isn't perfect here. I'm seeing functional values getting closer and closer to negative 1. So that would be the limit as x approaches -2 from the right. Now, as we mentioned in a previous segment, for a limit to exist, I have to approach the same value from both the right-hand side and the left-hand side. So this would be a case where the limit from the left does not equal the limit from the right. Therefore, if I gave you a limit as x approached -2 without a one-sided direction, I would have to conclude that this limit does not exist. So I put DNE for does not exist. Now, continuing on to look at the limit as x approaches 1. In this case, when I come over here to where x is 1, if I walk along from values less than 1, right, I'm getting closer and closer to 1, but I don't actually step on 1. And then I walk along this direction, right, and as I walk along, I'm looking up at these functional values, and I don't actually step on 1. So I don't realize that if I did step on 1, I've got this crazy thing where I have this open circle and the functional value defined elsewhere. So instead, if I stand very, very close to 1 and look at functional values, the functional values that I see are values that are very, very close to 2 in this case. So it doesn't matter that I have an open circle here. My limit as x approaches 1 is 2. All right, in a minute we're going to talk about functional values because what we'll notice about the functional value if I actually did step on 1, right, the functional value is different than the limit, and that can happen. Now I want to look at the limit as x approaches 3. So again, same kind of thing. All right, I do have an open circle. It's very exaggerated there, the way I drew it. But I'm walking up to 3. So you take a minute and conclude what this limit should be. All right, and I hope you recognize that we would see functional values that are getting closer and closer to 1. And I asked you to find limits in all of the places where strange things are happening in the graph, right? So we tend to not see a ton of cases where the graphs have open circles or these jumps. And so sometimes when I ask a student something very basic, like the limit as x approaches 0, nothing strange is happening at 0. And this would be a case where the limit is just the functional value. So if I just said, okay, well, what's happening if I walk up to x equals 0? All right, so if I walk up to the origin here, right, and I look up at the function, I'd have to estimate this one. It's not a nice whole number answer, but I'd be just less than 2. So maybe I'll estimate that at 1.7. So we tend to focus on these situations where there's a hole in the graph or where I have this piecewise function. A lot of our exercises ask you to consider limits in these cases, but don't forget, if I asked you for a limit, right, in just a normal graph, right, where nothing crazy is happening, right, then you could just find this limit, which is the same as the functional value at x equals 0. So speaking of functional values, I've also asked you to find f of -2. All right, so the limit as x approaches -2 does not exist, but the functional value, that would be the closed circle, right? So the functional value would be the value of -1. All right, so the limit from the right equals the functional value. And f of 1, the limit was 2, right? Because if I stood close to 1, I see functional values close to 2, but the actual closed circle, right, the functional value is up here at 3. So if I actually step on 1, right, or put 1 into the function, I get an output of 3. And f of 3, so if I look here at x equals 3, look up, I see this open circle. that tells me that the functional value does not exist.